Welcome back, compadres. I'm Brandon Tolbert, and today we're talking structural engineering. Previously, we worked through an example to determine the reaction forces of several components of an assembly. So we broke the thing down into free body diagrams and we determined the reaction force. Now that we've done that, this sets us up to determine internal forces. Why do we want to determine internal forces? Because this leads to stresses. What stresses are our components placed under? We have to know the internal forces before we can even predict stresses or calculate stress values. And so as a structural analyst, why is this important? Because we want to eventually predict the worst case stress location if we can, and then we compare that with the results of software, and if we get similar results, then we're good to go. If we don't, then we have to go back to our analysis and figure out what went wrong or what assumptions we made that were not correct for the situation. So that was a long-winded intro. So let's go ahead and get started. Welcome back. Today I'm going to show you a step-by-step approach to determine the internal forces using the cut method. In fact, we're going to go through 6 steps to do that. So I tried to break it down to make it easy. Hopefully you guys will understand this. So what we're looking at today is we're going to try to determine the internal forces at plane A of this assembly that consists of a rope and a member that's end-loaded. You know, this could be like the tailgate on your truck, and you could basically do a force analysis like this, but we're going to walk through it. And the key concepts I want you to focus on, it's going to be much the same as we discussed in video 1. We're just going to add a couple extra steps. So the key concepts I want to discuss are 2 force members, free body diagrams, the cutting method as we're doing here, sign conventions of internal forces, and once again the equations of equilibrium come into play. So let's get started. So much of the steps we do here are going to be the same as we saw previously. We want to identify the 2 force members because they can simplify our analysis. So if we look at this assembly, this rope and tension, it's only got 2 points that it's in contact with, so it's a 2 force member. So in general, cables and ropes are going to be 2 force members, and what you want to acquire from a 2 force member is the geometry. And so we can see here this rope is 4 inches tall from this datum point through the center of this member, and it's 5 inches long. And so you draw it here, and that's your geometry, and that's the 2 forces acting on that 2 force member. So in general, cables and ropes are always 2 force members, and it's easy to do an analysis on those. Step 2, draw the free body diagram. I can't stress it enough. You got to break it down into a free body diagram of each component. And then you replace the forces where they touched with equal and opposite forces. So for instance, this rope was hanging off of this hinge support, so the forces are going to be equal and opposite at those nodes of contact. So they're labeled the same force. The same for this node right here. The rope was pulling on the member at this location, so the forces are going to be equal and opposite. And you can assign these in any arbitrary direction. I like to put things in tension because we usually consider tension positive when it comes to stress analysis. So what you want to do is identify, you have 3 equations in your pocket, so you're looking for 3 unknowns and also a force to relate it to. So you can see here, member force 1, that would not be a candidate because you can't solve for anything since you don't have a force load on it. And then if you look at this member, guess what? We have 3 unknowns. This one right here, this one right here, and this one right here. And you have a force to relate it to. So you can definitely solve for the forces, reaction forces on this component. And the last thing I would stress is on these 2 force members, since you want to know the geometry, use Pythagorean theorem to calculate the distance right here. And so I just applied Pythagorean theorem, the height squared plus the length squared, and take the square root of that, and you get the square root of 41. And you can use this ratio to your advantage to help you calculate the forces down here, as you'll see in the next slide. Once you identify the member you're going to solve for, step 3 is to solve for the external forces for that body. So recall that we're doing this body right here. You have 3 unknowns. These 2 reaction loads and this this load right here relates to the 2 force member. Now you apply the equations of equilibrium, and I'm not going to go too much into the math, but you can apply a moment balance at this point right here, and you get this result. And then you can apply an equation in the equilibrium equation in the y direction, and if you do that, you can see here I have this ratio, and this is why geometry is important for 2 force members, because you can actually get the x component and y component of this 2 force member just by relating the geometry, the ratio of the geometries to the force. So this is actually going to be the y component of F2 when I multiply F subscript 2 by this ratio. So if I do that, and then I get an answer right here, and then you apply equilibrium equation in the x direction. It's the same thought process. I use the geometry to get the x component of F sub 2, and I can get an answer now. So once you've solved for the external forces, the next step you can do is you can actually solve for the internal forces. So step 4, to solve for the internal forces, you want to cut the body at the location of interest and draw a free body diagram. So that member, I cut it into location A right here. This is the left side, and this is the right side. So I have to, where I cut this at, I have to put in internal forces. And you generally have 3 internal forces that you got to write out. And in textbooks, they don't show it all the time, but if you get in the habit of writing out these 3 internal forces, you won't make too many mistakes. So I cut this member. Now I got to put a shear load on that surface, a normal force on that surface, and a bending moment on that surface. And so typically you can put these in any direction you want to, but as we go further along and build on our analysis, there's a sign convention that works really well, and this is the general sign convention that you want to put on your cut when you cut it. And so on the left cut, you generally want your shear force pointing down, your moment basically bending it up into a smiley face, and then your normal to be in tension, so that would be outwards. And on the right hand cut, you do equal and opposite, and so your shear is up, your moment is bending it so that you can roll it up into a happy face, and then your normal is in tension. And I've showed that here. So now you have 2 sides you can leverage, and generally you pick the easiest one to solve. You know, since this has easy components, I think I want to do this side. This one has, you know, a component that's I'd have to break down into x and y components, so that's a little more work. So I want to solve this side. This is the side I want to solve, and I have 3 equations, 3 unknowns, so I can solve this. And so generally what I want you to do is when you cut the beam, in summary, the main point is cut the beam, replace it with a shear, normal, and bending moment. Always, and you won't make mistakes. And follow the sign convention because it's going to be useful later on. Once you solve for the external forces, now step 5 is to solve for the internal forces at the cut location using the equilibrium equations. So we have 3 unknowns: our shear force, our normal force, and our moment. And so we quite simply just, it's pretty much should be clockwork by now, apply our equilibrium equations. In this case, first one I apply is equilibrium equation in the x direction. So it consists of this force component and the normal force, and I get this result. Then I apply my equilibrium equation in the y direction, and it's going to include this. It's pointing down, So it's negative and then minus my shear force, and I end up with this. And then I want to apply a moment at this location, and I get this result right here. So I was able to solve for all the unknowns with those three equilibrium equations, and those are my internal forces. And that's really bang. That's it, guys. So with the cut method, you're able to solve for the internal forces at a location, and it's real easy because all it requires is the equilibrium equations. And so the last step, number 6, would be to flip the direction vectors. So here's our final result. Because the values we calculated previously were negative, we have to flip their direction. So the moment was labeled counterclockwise, and we got a negative, so we got to put it clockwise to make it positive. And with the shear force right here, we got a negative, so we got to flip the direction upwards. And for the normal, we had it in tension, and we got to flip it to make it positive. Now it's in compression. So in summary, we applied 6 steps to solve for the internal forces at the location of interest using the cut method. These first 3 steps are steps we've seen before. Identify the 2 force members, draw a free body diagram of each component, solve for the external forces. And then these are the additional 2 steps we added in this video. It's to cut the body location of interest and draw the free body diagram, taking into account that you need a shear, bending, and normal force at each location you cut. And so that's the key point. And then you want to solve for the internal forces at the cut location using the equilibrium equations. And then finally, flip the negative force vectors. So guys, that should be a simple example. This can extend to more complicated geometries and assemblies and analysis. This is the fundamentals. If you understand this, you can move on to the next thing. And so that's what we're going to discuss later on. So guys, I hope you enjoyed this video, and if you liked it, please subscribe or please leave a comment. Tell me, guys, more about you and what you want to learn. I'm here to mentor you guys and provide my knowledge. I really am. And so you guys are the drivers and I'm the passenger. So you guys drive this thing. So thanks again, guys. If you liked it, subscribe, and I'll see you next time. Adios. There we have it, guys. With the cut method, you were able to determine the internal forces at a specific location just using the fundamental equilibrium equations. I mean, how easy was that? If that doesn't get you excited and want to learn more, I don't know what does. All this stuff is very fundamental, guys, and textbooks may not describe it to your good enough to you so that you understand what's going on. I'm here to simplify that process. And if you have any questions, guys, comment below. I'm really interested in what you guys think about this. And if you want to learn about something else, guys, I have a wide breadth of knowledge up here. So if you want to deviate onto something else, let me know, and I will take that into consideration. But for now, you guys rest up and keep working hard. I'll see you in the next video. Adios.